All right. Good evening, everyone. I hope you're doing great. It's good to see you guys again. Good evening. Good evening. In the chat. All right. I believe everyone can hear me. That's great. Okay, before we begin, I want us to take a quick recap of what we've done so far, especially what we did last week. I know it's been interesting so far. Yes, a little bit challenging and all of that, but in all, I do believe that you guys are actually learning. So today we'll be looking at data structures that will include arrays, hash tables, linked lists, and many other data structures. We will look at why data structure is important and the real life situation where you would want to apply some of these data structures. All right. I would like to share a link with us. So the link will help you with this class very much. Most of the things that we'll be talking about today is actually contained in the link, so you should do well to try and visit the link. All right, so the link will lead you to this particular page that is currently showing on your screen, but before we do that, okay, so I think let me just share the QR code here. Then I'll also call out the link. So here is the QR code. If you can visit the QR code. I mean, if you're watching on your laptop, you can scan the code with your phone. Otherwise, you can visit bit.ly/DSA-SD-DS. So you can, I'll call that again for those that may not have gotten that. bit.ly/DSASD-DS. You know what I would do? Okay. Let me see if I can share another screen that will show that in detail. Oh, okay. Yeah. One thing we can do is, let me utilize one of these screens to show you that. Just a minute. Yeah, I think one of these has an input feed where they can allow me to do that. Again, it's bit.ly/DSA-SD. SD is for software development, then -DS. So bit.ly/DSA-SD-DS. So that's it. DSA-SD-DS. Let me increase the size so that you guys can see it. So bit.ly/DSASD-DS. All right, just keep that on one side. We'll soon get to that part of the class. Okay. All right, let's get into the class. Before we do that, I would like to give some announcement regarding how the class is progressing so far, and some information that you will need from here on. We can go back to the slides for now. We'll come back to this this online tool later on in the class. All right, so for some announcement, I do hope that we all have registered on Canvas by instructor. Previously held classes have their presentation slides already uploaded there. I know you guys have been asking for the slides, the class materials, and also now we have all of that uploaded there. Once you have signed on and registered your name on Canva by instructor, you will go to files, and then you'll see the file structure already broken down into weeks, right? You have week 1, week 2, week 3, week 4, and each of them have their slides. And for those weeks where we dealt with some codes, we have the code bases also there. So it will do you a lot of good to actually get your accounts already set up. And in addition to that, I know we try to encourage chatting during the class, and that is still not discouraged, but for you to get better engagement when you are asking questions and all, you can actually use Canva by instructor. You can create discussion, and you can tag your instructors to answer whatever questions you have. I saw there today that some of you guys already started using that for asking questions, and other of your colleagues have been able to answer your questions. So that is good, and we encourage that to continue to happen. So from here on, also, we try and have some discussion on Canva by instructor too. So for content that we are not able to cover in the 2 hours of class, we extend that to Canva by instructor, and in the discussion we can have a better engagement and answer your questions. And if there are any blockers that you're experiencing, we will try to unblock you through the discussion. And also, you guys remember that week 2 we did our first assessment, which was covering TypeScript and setting up your ID. Then we used Google Forms for that assessment. But from now going forward, we'll be using the LMS, which is a Canva by instructor. So again, it is very important for you to have your account already set up. Actually, as of today, the modular assessment, which is the first assessment after the first module, will go live. So that will happen also on Canva by instructor. So do well again to get signed up. Read the instructions for the assessment, and you are given about 60 minutes to answer 50 questions. They are all multiple choice questions. So you just pick from A to D to answer the questions. And this modular assessment is very important because it contributes to your final grade. So you get graded by these assessments, and at the end of the day, you see where you fall into. All right. So after the modular assessment, for the assessment, we also continue. We will continue with our weekly assessment. Yes, we were not able to do some of this assessment last week and the week before that because we were migrating to this new LMS. But going forward, we'll have our weekly assessment. So this week we have been looking at algorithms, and we looked at big O notation. And today we will do the concluding part of the tools that helps us as software developers to write efficient software. Okay, so again, like I mentioned, yes, we have discussion on Canvas by instructor, but that shouldn't discourage you from asking your question in the comment in the chat section anyone that you get to ask, as much as I can, I will try to answer them. So we had looked at big O notation as a measure for running time of a piece of code. So big O notation helps us to measure how well or how fast our code runs. We consider various sorting algorithms as well. That was on Wednesday. And the purpose of doing that is to also help us cement the knowledge of big O notation. Your instructor did show you the different types of sorting algorithms there are, although that's not the exhaustive list of sorting algorithms, but those are like the basics that you can use to generally understand how sorting is implemented. And again, to point out, some of these algorithms, you may not have a need to re-implement them on a daily basis. I mean, the program languages that you use, some of them already possess libraries, or they already have inbuilt methods and functions that do some of these things. And those functions are already optimized to be the fastest way to sort and what have you. But the idea is for you to understand how these things work under the hood, right? You may not need to reinvent the wheel in most of the cases, but all is to afford you better understanding, right? So, big O notation and how the running time of each can help us to determine the potential impact and the choice we get to make when we are picking an algorithm. All of that is informed by understanding the efficiency of a particular algorithm that we are picking, and the efficiency is also informed by how well they run, which is notated by big O notation. So talking about making a choice, in computing generally we make trade-offs, right? Whereby you weigh your options and decide on what you can afford to allow and what you can't afford to overlook. So we sometimes have to choose between speed and the storage space. And a good example of where such a trade-off is being made is you look at your computer and you have your RAM. I believe we all know what a RAM is, random access memory that comes with your computer. Some of your computers are graded by this RAM that they have. Some will have 32 gig RAM, some will have 4 gig RAM and all of that. And if you look at how RAMs are built, they are built to be fast and they are expensive. And that's why your computer does not come with 128 gigabytes of RAM. Most personal computers you see around is around 8 gig to about 32 gig, and sometimes you come across 64 gig. But there's a trade-off in that. It is expensive to make RAMs, right? And there's also a limited space that a RAM can hold that will make economic sense to put in a personal computer. So you see where the trade-off is. I mean, it would be a lot better if you can have like a terabyte sized RAM. That way your computer will be super fast, right? But the trade-off had to be made. And same also applies to when you're choosing algorithms or when you're dealing with writing efficient code. We do make such trade-off in the case of writing programs as well. So there are some algorithms that you will pick that are fast for a given number of data points. So let's say you have 100 input data. There are some algorithms that are really efficient for such, and there are some that once the input size goes beyond a certain number, it becomes a really bad choice to use such algorithms, right? And we'll look at some of those. I will show you some graphs on the tool that I shared the link for earlier. And if you're just joining, I did mention that we should go to this link, bit.ly/. dsasd-ds, and there you will get to see the tool that I'll be using during this class. All right, so let's go ahead. So like I mentioned, some algorithms are better suited for a given data set, and they are better suited for a size of a given input data. And some algorithms, they tend to approach constant time. On Tuesday, we did talk about constant time, where we say some algorithms have O1 running time, right? Which means no matter how much input you have, it will keep that constant time. So there are such algorithms that for small number of inputs, yes, they will seem as if they are not really doing well, but as they approach bigger numbers, you begin to see them stabilize at a given constant value. So it doesn't matter if you have 2,000 or you have 1 million. The difference in speed is not so obvious, right? Okay, so also important to algorithm are how data gets stored. We also saw arrays at work during the last class, where we talked about sorting algorithms. So that's how data structure actually are used in real life. Although it wasn't really talked about so much, but for every of the implementation that you saw last week, in the last class, you'll see that arrays were really heavily used. So, and the arrays, they act like, I don't know if any of you have seen honeycombs, how they are stacked together, right? Arrays are like that. So they are in a contiguous location, which means if you see a data here, the very next slot of memory will contain the next data in that array. So contiguous location means that the address of each data point is one step away from the previous one. So just one step ahead, you get to see the next data point. All right, we will see the details as we get into the class today, all right? So what are we looking to achieve with this class? So again, the class is about data structures, and we look at some examples of data structures, okay? All right, so what are we looking to achieve in this class? We are looking to be able to pick the right data structure for simple problems, implement and explain the behavior of some core data structures, and understand real use cases of data structures on a daily basis. And in doing that, we'll be looking at linear data structures. You see arrays, you see linked list, you see stack, you see queues, you see binary trees, you see N-ary trees, you see binary search trees, all under tree-based data structures, okay? So again, our learning objective is to be able to, after this class, know the right data structure you pick for a simple problem, and also know how to implement those data structure. Again, I mentioned that some of these things are already implemented, that you may not need to reinvent the wheel, but being aware of their existence and how they work is actually required for you as a software developer, so that when you come in contact of some problems, you will know how to tackle them, and you know how to choose the most efficient method of actually solving such a problem when you do come across them. All right, so I'll take a pause here and sort of go through the chat to see if there are questions thrown my way already. All right, the link is shared in the comment section. Thank you for sharing that, so that you can also take a look around. By the way, you should try and play with that tool even after this class. And before the end of the class, I will give us a short assignment around the tool to see that we have a good understanding of moving around the tool. Okay. All right. I do not see any questions so far. Yeah, someone said they were invited to cybersecurity instead of software development class. Okay, so I think you should reach out to any of the admin, all right? Or in your squad, you can raise that up again. Okay. Right. That's good. No new questions on the chat, so let's get into it. So we'll start with some definition. We'll define what data structure is. A data structure is a specialized way of organizing, storing, and accessing data in a computer so that it can be efficiently used. And you can see, or you can say, a data structure is really important in getting efficient with your algorithms, because if you choose right, you will reap the benefit of choosing right. But if you choose wrongly when it comes to data structures, it becomes a headache to actually get efficient programs running. All right, so why do we need them? Before I get into that, data structures, yes, as defined, are ways of organizing, storing, or accessing data. Data structures helps us in many ways, actually. It helps us in many ways because on a daily basis, we have to deal with data. And having them structured properly impacts how we get to access them, impacts how we get to maybe even insert new data points or delete from those data points or even search for them, okay? So why do we need data structures? Why do we need to learn them? So data structures helps us to store data logically, like I mentioned earlier, and store them compactly. They help us perform operations such as searching, inserting, deleting, and accessing the data. So when you say search, you are searching and looking for a piece of data to know if it exists. And if it does exist, your search will return the location for that data that you're looking for. So imagine you're searching something on Google. The search result that comes back includes URL to where that information was sourced from, right? So that's how search typically works. So whenever you're using a data structure and you need to search for something, when you do search, it returns the location of the data that you're searching for. And then when we say insert, I said to perform operations like searching, inserting, deleting, and accessing data. So when we say insert, inserting is adding new data either to a specific location or have the data structure itself determine where new data should be. So there are some data structures that already know, or they self-organize, they already know where to have new data, right? Why some don't really specify, you'll be the one to specify what location new data should go to. Can also affect efficiency. Let's say, for instance, when you need to search, where your data is saved and how it is saved can affect or impact how efficiently you get to search for the data, right? So also deleting is removing a specific data from an existing structure. So you provide the location of the data, and then the data structure removes that data in that location. And then lastly is accessing the data. So accessing the data is getting the data in the data structure given a location. So you provide it with a location. Say you have location 1, 2, 3, you have location 1, 2, 4. So if you want to get any data from location 1 to 4, you provide the location 1 to 4, and then you go to that location and you are returned the value that is stored in that location. So all of these operations, searching, inserting, deleting, accessing data, are all part of the operations that a typical data structure will allow you perform. Okay. So another reason why we need to know about data structures, or why we need them, is it helps us solve problems in an optimized way. And I mentioned that earlier, that programming efficiency, algorithm efficiency, all are hinged on how your data structure is. Don't worry, we'll get to see some of this data structure. Although you're already exposed to the likes of array, which was used heavily in the last class, but we'll still go back to explaining them again, okay? All right, so the last thing is to support algorithm efficiency and code scalability. So if you pick the right data structure for a problem, it helps with having efficient algorithms, right? And it also helps you in scaling your code. Say you have a folder that contains 2 items. With the right data structures, a folder of that structure, you should be able to scale to having like 500 folders within another folders. So let's say you have 20 folders. In each of those folders, you should be able to have like another 500 folders in each of them. And it shouldn't become a headache trying to manage them, because your data structure already provide a basis for handling such. So you can tell what folder belongs to another folder, what folder is a parent to a folder, and what folder is a child to another. So all of that are handled by your data structure. So you can think of data structures like tools. So imagine you have a workshop. The way you arrange the data, or in this case, your tools, will determine how quick you can access them, how confidently you can put them back, and how easy it will be for you to give direction to someone. For instance, say, okay, go get me a plier. If your workshop is organized, you can easily tell the person where the plier would be, and they will go there to get the plier. So that's the benefit of having a good data structure, right? So the better your data structure, the better it fits the problem you are trying to solve, the easier, faster, and more reliable your solution becomes. All right. So let's jump right into it. And now we will be sharing the tool that we mentioned earlier. But I have like a summary of each of the data structures that that we'll be talking about. I have like a brief of them. So the first one we'll be considering will be arrays. So I did describe earlier that array is like a linear collection of elements accessible by index, right? And we have different use case for arrays. In sorting algorithms, we use arrays heavily. So let's say you have a list of users and you want to sort them by age, right? Or you have a list of the age of people in your community, in your class, and you want to know who the oldest is. You can use a sorting algorithm to do that. And the sorting algorithm will rely heavily on array as a data structure, right? Or you want to know who the leaderboard, or who is leading a leaderboard by scores. You can use array for that as well. Okay, so we go right into the tool now. Again, if you've not yet logged onto that tool, the link is in the chat section. Is bit.ly / dasasd -ds. The link again is in the chat section. You can just scroll up. All right, so before we do that, I will want to go through the questions again. So I see we do not have any questions so far, so I believe you guys are following well. Okay, so someone is asking which tool are we using. So the tool, again, you can access it via bit.ly /dasasd -ds. Let me see if I can share the QR code again. So the QR code should be on your screen now. So you can scan that with your phone. So I'll give us like a couple of minutes or seconds for everyone to be on the same page. And then when we'll come back, we'll jump right into it. So just a few seconds, right? So if you're just joining, there's a QR code on the screen for the tool that we'll be using to better understand data structures. So I will show you an example with arrays, and you can play around with the rest, but I will also explain how each of them works. So we'll be covering about 7 of them. I mean, for data structures, there are quite a number of them, and when you check that tool, you will see that there is a, okay, let me just jump into the tool and explain how the tool is. First, I'm currently zoomed in, so I will zoom out so that you can see what I'm showing you. Okay, I believe we are all seeing it now. So if you are viewing this on your computer, this sidebar will probably be opened, but because I'm zoomed in, I have to open and close it so that you all can better see what I'm showing you. So I mentioned that we'll be starting with array, and on the tool, there's a description of what the data structure is. For each of the data structure that we'll cover in this class, there's a description, there is a key characteristic of the data structure, and you have a sample code. Although it's not a working code, but it shows you how, or the idea behind the implementation of that data structure. And then we see the time complexity. Time complexity essentially is big O notation. So time complexity tells you the growth rate of the running time of that algorithm. And what does that mean? When we say an algorithm is ON, it means that the time for executing, or the running time, or the time it takes for that algorithm to run from start to end, is dependent on N, and N is the number of data input. So if you have 2,000 data to work with, then the time it takes for that algorithm to run will be 2,000. Let's say in this case, it takes 1 second to go through one data, then it will be like 2,000 seconds. But in real life, algorithm measurement really doesn't work like that. You can't really say, oh, I want to set a stopwatch to measure algorithms and how they run efficiently. It won't give you accurate measurement because a lot of things are dependent on that. So imagine you are using your computer now to do that measurement. Whatever measurement you get on your computer won't translate universally because while you are doing your test, it could be that there is a background process running that is causing your computer to slow, which will mean that at the end of the day, you have a slower time. It could be that you're running on a 2 gig RAM computer and someone else is running on a 64 gig RAM computer. That will impact the time it takes the algorithm to execute. But with big O notation, it skips through that entirely. You guys should let me know if you can't see the screen properly so that I can zoom in. But I believe we also are following on our individual screens. All right, so again, big O notation helps us to sort of standardize how we measure the time complexity of an algorithm. Again, time complexity is essentially saying, given this number of inputs, how long does it take or would it take in the worst case scenario for this algorithm to run? So in a case where the algorithm is ON, it simply says that as the number of inputs increases, the running time also increases. So it's dependent on N. So where you have N squared, I know in the first class, your instructor did mention a loop inside a loop would cause an N squared time complexity. And why is that so? Because if you have, again, for instance, 2,000 data points, and you have 2 loops, which means you will run the outside loop 2,000 times, and for each time you run the outside loop, you run the inner loop 2,000 times. So that's 2,000 raised to power 2. But if we are to use time complexity, that would translate to O(n) squared. So no matter the number of inputs, it could be 10,000, it could be 20,000, it will always be that O(n) squared, where N is standing for 20,000 or 2,000 or whatever the size of inputs you have. So in the case of arrays, like I mentioned, they are stored in a contiguous location, in a contiguous memory location. So if you have your first array stored in memory location 125E or 125E6, then the next one will be like 125E7, depending on how memory allocation is done for each computer. Well, let's say theoretically, or in a standardized way for everyone to understand, arrays are described to be zero-based data structures, which means their first element starts from 0, then the next one will be 1, the one after that will be 2. But all of this abstraction will have its own implementation depending on the computer or the architecture of the computer. But to describe it, you can see it as, array 0 is the first element in the array. So of interest to us in this class, right, is to know the time complexity for some of the operations that you can perform on this data structure, and we'll do examples for each of them. So for accessing a data on an array is a O1 complexity. And if you cast your mind back, when we say something is O1, it means that the time is constant for whatever input you are dealing with. So if you have an array of size 20,000, which means you have 20,000 elements in it, to access a data on that array takes the same time, whatever the case is, 20,000 elements in the array, 2,000 elements, 2 elements is about the same time that it takes. And why is that? Because you are providing the location, and when accessing any element, it just goes straight to the location and pull the data out. It's not like it's starting from the first element and then looking and searching and searching. It already knows where the location or where the element or where the item you're looking for is based on the location that is attached to each data point. So you just provide the data location and then it fetches it out for you. So it doesn't really matter how big the array is. The access will always be O1. Okay? And when you are searching in an array, it will be dependent on the size of the array, because in your search, you are not providing memory location, you are only providing value. So, which means the array will have to be traversed one after the other. Every element in the array will have to be looked at. So in a worst case scenario, if you have 2,000 elements, it will take about 2,000 steps to search out a data. But in the best case scenario, if you're so lucky that your data is on the first index, which is index 0, so when it starts, it gets to see the item you're looking for. So in that case, the best case scenario is like O1, which means it's a constant time, right? So it takes about just one step to get to search through an array. And insertion also takes an ON, because the number of elements in the array determines how fast you get to insert into the array. And why is that? Because in arrays, they are typically fixed sized, right? So when you are dealing with them, unless your programming language is allowing you to specify dynamic arrays, which is the case for JavaScript. Like you can specify fixed arrays, you can specify dynamic arrays. By fixed array, we mean that as you are declaring the array, you are already saying the number of items in the array. So if you want to insert inside an array that is already fixed, which means you have to expand the array. And in expanding the array, you are actually copying one array into a bigger array. So if you have 2,000 elements, that means you have to transfer 2,000 elements, right? So insertion in that case might be dependent on the number of elements you currently have. All right, all of these are rather details that you can also figure out or read on by yourself, but I just want to dwell on it for this particular data structure, because as we go subsequently, I may not need to dwell on that. You get the idea of what accessing is, what searching is, what insertion is, and what deletion is. Same thing applies to deletion, right? You have to search for the elements you're looking for, and then depending on how the array is, you may need to shrink the array, right? After removing an element. So let's say you have an array of 10 elements and you delete an item from position 5. Position 5 will not be empty. That position will have to be taken up by something else. So the process of moving elements forward, right, to fill up the space where you just removed an item from is dependent on the number of items in the array originally. So if you have 20,000 items in the array and you deleted something from position 2, which means you have to move every element starting from position 3 up till position 19,999 forward. So that's about 19,997 moves that you have to do. So it's dependent on the size of the array. All right, so I will take a pause and look at what we are saying in the chart. Again, if you're just joining, the LMS allows you to have a better conversation because you can start a discussion and the discussion wouldn't end on the live, I mean, as is the case of YouTube, that whatever you're saying is just limited to what is being said while the class is happening. But with discussion, you can have conversation that extends beyond the class. And that way, many people can even give you contribution to whatever questions you are asking. Okay. Okay, so I'm still looking through to see if there are new questions. Okay. I can't see any questions, so we'll move on. All right, so where do we apply array, for instance? You can use it in storing data, in data storage, so storing collection of related data, like we've seen during the sorting class that we have. So related data were actually stored in an array and then sorted, right? You can use them in matrix operation, and when you're doing multiplication of matrix, and the parallel application of matrix operation. Matrix operation goes beyond just what you learned in probably your math class. There are several operations to that. In string operations, say you want to manipulate a string, the low level implementation will be that you break that string into an array, then you begin to manipulate it, right? So if you want to find the first letter in a string, for instance, that string will provide you an array structure that will be able to, that will also allow you to access each element in the string. So you want to change the first character of a string to capital letter, for instance. You can just do an string square bracket 0, which will be referencing the first element in that string, and then you can transform it by using, say, to upper or whatever method your programming language provides you. You can also use it for lookup table for fast access to pre-computed values. All right, so here are the graphs that I mentioned earlier that I was going to provide you. So in terms of access, I said it's O1. So it's one to access the last element or the middle element. But when it comes to searching, like I mentioned, is dependent on the size of the input. So this graph will better make you understand what we mean by the fact that the growth rate is linear. When you talk about linearity in mathematics, again, it's not like you need mathematics to understand this thing. You can just apply common knowledge to understand them. When we talk about linearity in mathematics, it means that one element, as it grows, it causes the other one to grow in the same equal amount. So while you are at 0, you are at 0 here. While we are at time 36, I mean, you have the same growth coefficient throughout the entire graph. So that's what we mean by linear growth rate. We have other growth rates as well. It could be logarithmic, it could be tangential, but all of those you can dabble into understanding them better. I think they will be beyond the scope of this class, trying to explain the mathematics or behind them. But you can just take a look at the graph and to provide you with good understanding. So if this is just straight line, as we have it on the screen right now for standard access, you know that that time is not changing. But if this is starting from small and is growing continuously at the same rate till you hit the n, which is in this case 1000. So if it grows like that, you know that is dependent on the size of n, like it's directly proportionate to the size of n, right? So if your n increases, the running time also increases. All right, so that's that for explaining the running time for each of these operations that you carry out on a data structure. Again, I dwelt quite a bit more on this so that we can understand the basis for explaining every other data structures that we have for this class. So here is an example of array in action. So let's say we want to access position 4. So position 4 in this case would be 0, 1, 2, 3, 4. Would be 5. So the results should be 5 when we try to access position 4, right? So access, and it alights 5. So let's see if we can access position 3. In this case, it should be 4. So click on access, it shows 4. Let's access the following. If I type 0 here, what value will it give me when I click on access? Any response? So it gives us 1. Again, because, yeah, thank you, Media Combi. It gives us 1 because array are 0 based. So they are 0 based. So their index starts from 0. Okay. So when it comes to searching too, and again, I will come to the aspect of this graph and I will show you why that graph is needed, or what it explains actually. All right, so you guys can take the next 5 minutes to attend to your attendance, and I will try to repeat what I said in the previous 5 minutes while my mic was somehow muted. All right, welcome back. Okay, so I'll do a quick recap. We were talking about arrays before we went on the break to take attendance. And I was told for the last 5 minutes before we took our attendance, I was muted. So I'll try to go over the things I was talking about. So I was describing this graph here, which is measuring in real time how this algorithm, how this data structure is actually performing when it comes to these four operations of accessing data, searching data, inserting into the structure, and deleting data from the structure. So I will perform some operations, and this graph here will actually be populated. So let's start with deletion. So as I delete, you see that the graph is being populated with data points, and you see another point in the data now. So as I continue to do that, you see that the graph changes. So I was explaining that theoretically, deletion should grow with the number of inputs we have. And we can see it actually does, because we see a decline because our input data is actually reducing. We see a decline. So let's say we have much more data. We still see this decline, but is also related to the number of items in the data. So the higher the number, the higher the running time would be. Okay, so same thing is with insertion. So let's insert some data now. So I'll just insert to the beginning of the structure, and then let me go to the end of the structure, insert some couple more data. Let's change the data so it's not like it's just one data we have. Insert and do more insertion. And by the time you check the graph for that insertion, you see it's actually reading the time it takes. But like I was explaining earlier, there are many factors to this. It could be that my system froze, or there are many other things that has been run in the background. But the expectation is that as you have more data points in your structure, the running time should grow linearly with it. I mean, if we do this a couple of times more, we will get to the point where we begin to see in actuality the linearity in the growth time. Or we just keep doing this. And you see that there is a pattern that is coming out now. Pattern that is forming now. That when we started, it seems like there is a constant time, then that value shot up, and again it shot up. So if we continue with this sufficiently, by the time you are plotting the graph, you see that there is a linearity forming, which also speaks to the worst case measure we had for insertion, which is in ON. The time complexity is ON. Okay, so that's that for insertion. And when it comes to searching too, let's search for some random numbers. Let's start with 128, and then we search for 12. So it has found 12. Deletion, because the graph changes based on the number of items in there. So let's search for 12 again. Okay. Search time. Let's delete more. Then search again. So right now it's saying it's taking constant time, but like I mentioned again, the more of it you perform, the more the true nature of the graph comes up. Let's search for some other number, 128. Or we search for more numbers. We have 123. But we do get the idea anyway that, I mean, how to use this aspect of the tool for seeing how these different operations are being impacted. And when you do an access, like I mentioned, you see that it already started with a constant time. Accessing is an O1 operation. All right, so let's go to the other data type. Let's go to, data. Data. So here, you can read the definition. I won't bother too much about that. But the key characteristics of linked list is that it has dynamic size. It can grow or shrink as needed, unlike arrays that in most implementation, they are fixed. When you want to define arrays in some programming languages, you have to specify the number of elements the array is going to take before you start to use the array. They are node-based, which means each element is stored in a node. So there are nodes in the data structure, and each node points to the next. So each node is not just containing data. Each node contains address to the next data. And you can see how useful that would be, because from wherever you are in the data structure, you can easily tell what the previous element is and what the next element is, right? Okay. So it has a sequential access to like arrays, right? It's memory efficient by the fact that it is stored contiguously to almost like arrays. It is flexible, easy to insert and delete elements. Also, like, better than arrays, I would say. And looking at the complexity, it already speaks to the efficiency of insertion. So if you're inserting at the top, is an O1 operation, versus if you are inserting at the tail. And the reason for that is that it's almost similar to what I explained when it comes to arrays, because you have to move elements over to adjust them, right? That will now impact the efficiency of insertion and deletion. But for accessing and search, it's ON. And then you begin to see the contrast it has with arrays. In arrays, when you are accessing, is an O1 operation. So if you're picking this data structure to solve an algorithm that will require a lot of accessing, you can begin to see that this may not be the best for that, because as the number of data you have grows, the longer it takes to access data in that data structure. But if your use case requires that, or all you just want to do is to search and insert items into the structure, it will be beneficial for you to actually consider this, because it has an advantage in that in a good case you can really get O1 an O1 situation going on. So here we have more or less like a pseudocode explaining how to implement this. I mean, yeah, this will work. Yeah, I think this will work. Just that you may not be able to visualize it as we have in the example below. The complexity grows. The graph speaks to those, like we explained it when we were dealing with arrays. So you can look at that and use that for comparison. I think I need to update this graph. It's not really stating correctly how that, but do look out for it. They will get updated. I mean, I'm still working on a lot of this other data structure, but I just want to keep it focused on a few of them. I mean, as time goes on, all these are going to get updated, and for your learning, you can always come back here to learn. I mean, there are other tools out there, but I feel like this is simple enough for guys just starting out. So you can always come back to this tool to visualize how these data structures work. So let's interact with this a bit. So here you can insert at the head, you can insert at the tail. So let's do this insertion, insert at the head again. So inserting at the head means that it's going to attach it to the start of the list. So let's insert 5 at the tail. So 5 is going to be behind. Let's insert 12 at the tail. It's going to be behind. We can and let's delete by another value, 3. And you see 3 is gone. So in this case of linked list, it has to search for each node to know what the value is, right? And then it performs deletion. You can also clear, and it clears everything. So let's quickly move to the other ones. I think we have about 5 more, but these ones we are just going to be fast with them. I think we already get the gist of the tool and how to use it. So in a stack, so a stack is called a LIFO data structure, and what a LIFO data structure is that the last in is the move out. Or let's say you put some balls in a container that is whose circumference is about the size of the ball. So it gives you a stack of balls, right? So the last one that gets into it is the first one that gets out. And there is a reason for this principle. Elements get added and removed from the same end. There's a reason for it. There are some advantages that it provides. So let's look at the characteristics. Life order. So the last element added is the first to be removed, and there is a single access point. All operations happens at the top. It has fixed capacity. So your stack needs to get a size, right, when you're defining your stack. And there are other cases where you can make it dynamic, and just as the case of arrays, there are programming languages that allows you create dynamic arrays, right? There is no random access provided in stack. Every element has to be accessed from the top. Here again is a sample code of how a stack works. So in a stack, you are either pushing or popping, or you can pick to see what the top element is, right? And you can also check if the stack is empty. So all the operations in a stack is about constant time, because all you are dealing with is the element at the top. So it takes the same time. So if you are pushing to the top, it takes the same time. If you're popping, you are popping from the top. If you're picking, you are looking at the topmost element. So it takes the same time. All right. All right. Applications, you get to see them in programming languages. I mean, as you guys advance and you're dealing with errors and all, there's such a thing called call stack in programming languages, and it's the order in which your program or your code is being executed, right? And then when an error occurs, it shows you the stack, the error stack, which is more or less like, oh, the last thing that happened is what it shows you first, and then it continues like that until it reaches the first, or let me put it the other way. The first thing that happened, which is like, oh, what recently happened, is shown first, and then it continues in that reverse order until it gets to the first thing or the last element in the stack. So again, visualize it as a cylinder containing balls. So the first ball is shown, and then it continues to pop until it gets to the very last ball. And you also see this heavily used in editors, and we will demonstrate that, right? When you are undoing and redoing, that's a stack in action. I think we should just jump right into the demonstration. Like I mentioned, the execution time is in O1 for most of the operations that it performs, which is a push, pop, and to pick. So let's play around with the tool. So I'll just type some random words. The essay is lit. So you see here in the stack, it started with D, and then DS, DSA, and then there's a space here. There's a space after this. Then DSA I, then DSA ID before I did a backspace. So I did a backspace, and then it gave us DSA I, DSA is space, DSA is L, DSA is LI, and then we have lit. So if I undo now, the stack. So you saw that the topmost element on the stack was this. So when I undid, it popped out. If I continue to undo, it will continue to pop it out. And if I redo, it's going to do that in a reverse order. So you see that the top is at the bottom here. So it's going to pop the top back. So redoing, we take this element back until we get back to DSA is lit. I mean, that's how your undo, redo actually works in theory. So that's that for a stack. So now if you were to implement, say, a code editor, and you want to do undo and redo, the best data structure to go with let's look at queues. So I'll just do a definition and then we'll go right straight into some demo. Probably we'll look at some characteristics as well, and then look at some key operations that it performs. So this is like a reverse of a stack. It's a linear data structure like we have with array and likes that follows the FIFO principle. So first in, or you can call it FIFO. So the first element in is the first out. So think of it like you're in a supermarket and you want to buy something and there is a queue. The first person that gets in is the first person that gets attended to, unlike in a stack where is the last element that got in that will be first attended to. So elements are added at the rear and removed from the front. If you think again about having a queue, let's say at a bedroom or a public restroom where there are a lot of people and a lot of people are trying to use the restroom and there's a queue, is the first person closest to the door of the bedroom that gets to use it first, right? And new people join the queue at the back, right? So some key characteristics is that the first element is added. The first element added is the first to be removed, like I explained. There are two ends, unlike in a stack where there's just one opening, which is at the top. So there are two ends. You start from the front for removal, and insertion is done at the rear. So when we are performing or deletion or insertion, deletion is done at the front and insertion is done at the rear end. So there's also no random access like we have with stack. All right, so with a queue, you have such method as enqueue, which adds elements to the back, and the queue, which removes elements from the front. And you can also pick, so you see the element that is at the front, just the same way like you have it with stack. And for those key elements, which is enqueue, the queue, pick, they have constant running time. So it doesn't matter how big the queue is, it will have the same constant running time, which is O1. Okay, some key application is task scheduling. So the example we have here is we are going to see like a task scheduler, a print queue. So if you have a printer and you send multiple jobs to the printer, is the first one that got into the queue that will be printed first until it gets to the last. Then we have this also being used in BFS, messages queue, event handling when it comes to event programming. I know we talked about event programming at some point. Okay, let's jump right into some demonstration of this. Okay, so let's say I want to make orange juice. What will be the steps for me to make orange juice? go to the market. So I'll enqueue the elements from the back, right? So we are inserting elements into the stack. So go to the market, locate orange sellers, enqueue that, buy oranges, enqueue that as well. What will be the next step? Will be to maybe go home. Then wash oranges, enqueue that, juice oranges, enqueue that, and enqueue that. So when we start processing this queue, like I mentioned, is the first thing that the first element that gets attended to first. So process, which is the queuing, we see that go to market is off. Then if we process again, locate orange sellers, we go off. And then buy oranges, we go off. Go home, we go off. Wash oranges, juice oranges, and drink orange juice. And we have our queue tended to with that. Now the queue is empty. So that's that for queuing. So like I mentioned, applications will be like if you have a task scheduler or you want to build a task app where you have some set of tasks to execute in a particular order, right? So we use this stack or queue when order matters. All right, so let's jump to some tree-based structures. So far we have been talking about linear data structures where elements are stored in a contiguous manner, right? So the next one we'll talk about tree-based structure. But before I do that, let's get to our chat section if there are questions. And sorry again for the audio that keeps going off for no reason. It just kept happening. I'm sorry about that. Okay. I'm just going through to see if there are questions. Okay, I don't think there are questions. Okay. Again, this tool, you can play with it at any point in time. And if there are questions that you have, you can always jump into the discussion section in the LMS to ask your questions. All right, so let's go to the next set of data structure. So when it comes to tree-based, by the tool, I have organized the data structure in different subcategories. So there are general trees where you talk about N-ary trees or binary trees, and then we have. All right, so let's start with some binary tree. After the class, you can go through the list. The list again is not exhaustive. It's not like this is all the data structures that exist in the entire world, but it should serve as a good basis for your learning. All right, so binary trees, by definition, they are hierarchical data structure where each node has at most two children. So there is a restriction as to the number of children that a node can have. Remember, we did talk about what a node is, right? So a node is like a point in the structure. When we're talking about a linked list, we said a node contains the data and also has the address to the next location. So in this case, each node can have two children. You'll get to see what we mean by children when we get to the demonstration part. So in this case, the child is referred to as left and right children. So there's a child on the left, there's a child on the right. Unlike in a binary search tree, there are no ordering constraints on the values. We get to touch on a binary search tree. Hopefully, the time we allow us. Well, we'll get to it. But in this binary tree, ordinary binary tree, order is not key. So data can be attached to any point. But when it comes to binary search tree, one of the benefits you get with that is as you're inserting data, it is self-organizing. I mean, that is for binary search tree. But in just ordinary search binary tree, you get to specify where data get to be put into, right? So characteristics, hierarchical in structure. It has left and right children, root node, leaf node. So leaf node is like the terminal node. I'll show you all of that when we get to the demo. So there is a parent-child relationship, and like I mentioned, there's no ordering constraint. So in a tree, you're able to insert, and the insertion, you can specify where, left or right. You can search, and yeah. I mean, you can delete as well. You can access like every other one. But those are the bases: insertion, deletion, search, and what have you. All right, so let's jump right into seeing the example real life application of a binary tree. Or just a general demonstration. We'll get to also see how it is. All right, on the tool, you see a fixed data that is already on the tool. It's starting with 50, 30, 70, 20, 40, 60, 80, and so on and so forth. So when I was saying that there is a left and there is a right. So for 50, there is a left, which is 30 to the left and 17 to the right. And then 20 to the left, 40 to the right, 60 to the left, 80 to the right. In binary search tree, I did mention that there is a constraint on how data is meant to be ordered. So if given a binary search tree, this is how data would appear there. But again, we are still looking at binary tree. So in a binary search tree, ordering matters. So smaller data goes to the left and bigger values to the right. That's how the ordering happens. Anyway, let's play with this tool. Let me zoom out so that you can see it as a whole. I believe you guys are also playing with this tool as we go along. So here you get to specify where you want the data to go to. So if you say to the right, data will go to the right here. So insert, data has gone to the right. If you keep inserting to the right, say 14, insert goes to the right. Let's insert something to the left, insert, and that's it. Let's keep inserting. And let's insert 11 to the left again. Insert more data, 15. So you see how it keeps on going. 17, and so on and so forth. And if you want to search, let's search for 13, which is not there. It won't find anything 13. So let's search for 34. And then it returns the node where 34 is. So it already shows that, okay, I found 34. Let's search for 70. It found 70. I mean, and so on and so forth. You can keep playing around with the data. All right, so that's that for binary search tree. We will talk about that's that for ordinary binary tree. We'll talk about binary search tree after we talk about N-ary tree, which in its case, we can easily use it to demonstrate a particular use case. And when it comes to binary tree, you use it in your file system. But for N-ary tree, by definition, is more suited to the left here is a structure that would benefit from a tree, right? So when you build such a menu in your web app, you really benefit better if you utilize a tree structure, right? Okay, so N-ary tree is like a binary tree, but it's not limited to just two children. You know, in binary tree, you said you can only have a left and a right child, right? But in an N-ary tree, you can have multiple children per node. So by characteristics, it has multiple children and so on and so forth. Let's look at a sample implementation, right? And you can all look at the time factor. But I think more importantly is actually seeing it at work. So like I mentioned, you can use this to build like a menu structure. And I believe that some of you will be excited to see that, oh, okay, so each time I interacted with a menu is actually this data structure that is in play, right? So here you can collapse and do all of that. I mean, those are just like added to the top, but the major part is that a node, in this case, is project, and it has source as a child, it has public as a child, it has test as a child. Now you see that it's not just a left and right child situation like we had in binary tree. It's able to have multiple children. It even has readme, has git ignore. All of these are the children. And in source, which is a child of project, you have pages, you have main TS, you have component. I'm very sure you guys are familiar with where this comes into play. So let's say you're building your own code ID, your code editor. You probably do something like this. And I do know that you have seen this similar structure. So this is implemented with a N-ary tree. Here you can even add, new nodes. So let's say we add code is good as a folder. So here, code is good becomes a node, and inside this you can keep adding stuff. You can add another folder, and so on and so forth, and so on and so forth, as much as you want, right? So I added hi as a file. So in this case, you know, I was talking about leaf node and all. In this case, hi becomes a leaf node because you cannot add new children to it. So it's like the end of that tree. I mean, think about a physical tree. A physical tree has branches, and at its end are leaves. So a leaf cannot have branches, neither can a leaf have more leaves, right? So in a tree structure, it terminates with a leaf. So that's that with that. You guys can play with this, play with it as much as you want. So let's quickly look at search trees. And like I said again, this list is expanding, but for the time being, for this course duration, I think we'll keep it at these basics so that you guys can go and tinker with it and play around with it, and I mean, just to get better understanding of how to use these data structures and where they serve their benefit. All right, so this is binary search tree. By definition, it's a binary tree, right? But in addition to that, it has some beneficial constraints that it comes with. And those constraints are that data are arranged in a particular way, right? It still maintains most of the characteristics of an ordinary binary tree, which is that it has a child, a left and a right child, right? And it cannot have more than that. But the benefit lies in that when you are inserting into the structure, there is a rule, we can say a rule, that ensures that data are appended or inserted in an orderly manner. And you see that here in the sample data here. But before we go into that, one interesting thing with binary search tree, and I think which is also characteristics of sorted data, is that the performance gets better, or performance approaches a constant time as the data set becomes bigger. You see, we started with 0 here, and then there is like a parabola. And what the parabola means is that for slight variation in the data size, you see a huge jump in running time. And that jump continues, then begins to stabilize. I mean, if you were doing small operations with like 100 items, and you see this graph, you'll be like, oh, this growth is really, really astronomical, because looking at the tangent of the graph is almost as if it's up. I mean, it's not just linear. It's almost as if it's shooting up, but that initial sudden growth normalizes as it approaches higher data points. And I find such algorithm quite interesting, because as your data increases, their efficiency sort of seems to normalize. And that's the case with binary search trees. So let's play around with this tool. We insert numbers. So let's insert, and I want to see if you guys can guess. I want to insert 25. I wonder where that will go. So let's insert something less than 20, 19. See, it's already sorting it out. Let's insert 18. Let's insert, say, 45, and we see where that goes. You see, it's already sorting, like, it's already arranging the item. Unlike an ordinary binary tree. I mean, let's keep inserting numbers. Let's add 42. 42 is going to join where 45 is. Let's add 47. And there are different approaches to actually reading a binary tree, but you get the idea that it sorts or puts things in order. You can see the pattern that it's already forming. Like 30 has something here lower than it, and on the other side is something higher than it. So if you're reading numbers, you read left first, so 18, 19, 20, 25, then 20, 30, 40, then go to 50, then you go to 50, which is the top of the node, right? Then you move to the right hand side, start reading from here to 60, 70, 80. I mean, you already see the pattern, and I find it quite interesting. Anyway, so that's how it works generally. So let's search. Let's search for 47. So search, and 47 is found, and it tells you how to actually get to 47. It tells you that, oh, it's on the left, or is on the right, left. So that's how the search happens. So it started from the left, went to the right, and then to the right before it got to 47, right? You guys play around with this tool, at least you get to understand these basic ones. And as your career advances, you get to learn even more complex ones. Today's state of AI benefits greatly from the fact that we are able to convert natural language into a vector form that is stored in a multi-dimensional array that facilitates all of this LLM that we are playing with. So that's the extent to which data structures are actually important. So once you're able to identify a problem, then find the right data structure for it. I mean, you can make really great advances in computing and solve even novel problems, or problems that had not been solved before. So those are the advantages of actually learning these tools. So play around with it, and get to understand it better. And that's it for our class today. Again, as a form of announcement, the modular assessment will be going live tonight. So watch out for that, and you'll have like a week to attend to it. So by this time, before this time next week, Friday, the assessment will be closed. So do well to ensure that you are registered on the LMS and ensure that you actually do the modular assessment, because it contributes to the final grade that you get. So it's very, very important. So it's about 50 questions to be answered in 60 minutes. They are all MCQs, so multiple choice questions. And they are all from the classes that we've taught, majorly from, go through the instruction, you'll see, majorly from week 2 and week 3. So those are still very, very simple classes. So, and if you need to review, you can go watch the videos again. All right. Good night, guys. If there are any questions, you can drop them in the discussion. I'm going to create a discussion for this class. And what I want you guys to do is play with these tools, ask questions where you are confused. Also look out for that discussion group on Canvas by Instructure. So do have a wonderful night, and we'll see you next week, Tuesday.